Thank you, Sangil. I'm going to talk about some work from several years ago, joint with Imre Bárány and Julian Barreau. I think it's not very new work, but I think it's very interesting, and I had some reason to think about it again recently. So a convex lattice polytope is a convex polytope with an integral vertices. And the questions that I'm going to discuss today are how many lattice polytopes are there under appropriate additional assumptions, and what do they typically look like? But before I make it more clear what I mean by these questions, let me talk about where kind of the genesis of these questions and where they came from. So we say that two convex lattice polytopes are equivalent if there's a lattice-preserving affine transformation that carries one to the other. So for example, here we can rotate by 90 degrees and shear to get from the first to the second, so they're equivalent. The third one, even though it has the same volume as the first one, isn't equivalent because there's no lattice-preserving affine transformation that would take it to either of the other two.
So what does lattice-preserving mean precisely?
It means that it carries integers to integers, or integral lattice points to integral lattice points. Yeah. So you can't do an arbitrary rotation or an arbitrary shear. It has to be very special. And so Arnold asked in around 1980, what's the number of equivalence classes of d-dimensional lattice polytopes of volume at most V? He gave some bounds on the log of this number, which in the plane. And Kanyagin and Sevastyanov generalized his proof to all dimensions. And then later in the 1990s, Bárány and Pach, and later Bárány and Vershik removed the logs from the upper bounds here. So there's still this double arrow notation here means that it's less than equal to some constant times that. So there are two different constants in the lower and upper bounds, and these are in the exponent, so there's still quite a large gap there between lower and upper bounds. And one interesting question that's open and probably hard is to close the gap, at least to get the log asymptotic bound there. But so the first step of Arnold's proof in the plane was to take an arbitrary lattice polygon and find an equivalent one inside a box. And the key to the improvement of Bárány and Pach is to find a box that's smaller. So here we say, given any lattice polygon, we can find a lattice-preserving affine transformation that carries it into this particular box. And here we've basically improved the situation by a square root in terms of the area of the box at the cost of not knowing exactly what box we're dealing with. We have to consider basically 4V different boxes depending on what A and B are. Hence, to obtain an upper bound, this should be a 2 here, not a D. To obtain a upper bound on the number of equivalence classes of lattice polygons, it's enough to bound the number of lattice polygons inside of a rectangular box. So how do we bound the number of lattice polygons in a box? Well, here's a lattice polygon. We chop it up into 4 convex chains. So it's guaranteed to be a convex polygon. So there will be extreme points, and we choose one of the points with smallest x-coordinate, one of the points with largest x-coordinate, one of the points with largest y-coordinate, and one of the points with smallest y-coordinate, and chop the polygon up into 4 chains. So it's enough to bound the number of lattice convex chains that connect 2 points, say 0, 0, and x, y. And what's a lattice convex chain? Well, we say that the slope is increasing monotonically along segments and is connecting integral points. And so let's let P of n comma n be the number of lattice convex chains with endpoint n comma n. I'll come back to how do we exactly apply this to bound the number of equivalence classes of lattice polygons. It's pretty simple. So Bárány and Pach gave upper bound of n to the 1/3, m to the 1/3. And if we combine that with the box lemma, then we can bound the number of polygons. First, V here is, the first V is the number of choices for A and B. So we start with an arbitrary lattice polygon and we find one that's equivalent inside a box. And we know that for one of the values, say A is between 1 and 4V, and B is 4V divided by A, that there should be an equivalent polygon in one of those boxes. V to the 4th is the number of choices of 4 points. So these are candidates for the extreme points of a polygon. So we need to find 4 extreme points, and we just take all sets of 4 points as candidates. And then e to the 1/3 V is the number of convex chains that can connect, for example, well, we have, if we put A in here and B in here, then we know that A times B is 4 times the volume, so we have A times B to the, is V to the 1/3. And that's where this factor comes in. And when we take the logs, all these polynomial factors just wash out. Later, Bárány, there are 3 independent proofs given. So that this is kind of background to the question that I want to talk about. This is not really the question that I want to talk about, but there were later, it does lead to the question, well, maybe we can determine actually the constant in front of this asymptotic bound. Once we know that it's bounded above, once we know that the exponent is bounded above by some constant times a function of n and m. There were 3 independent proofs given in the 1990s of what exactly is the constant that belongs there. And then more recently, Julien Barreau and Enrique gave an even more refined bound that controls the error term. Again, this is in the exponent, so it's this is not quite as good as determining the asymptotics of the quantity Pnn, but they wrote some explicit function for this and showed that bounding the error term is equivalent to the Riemann hypothesis. So, kind of following the work on Arnold's question, Vershik showed, or asked the question, is there a limit shape for these convex polygons? So what does a limit shape mean? So what we're doing basically is we start out with a convex lattice polygon in this square 0 to n by 0 to n. Then we're going to scale it down so that it's in the units square. And the question is, if we take n to be large, is there a shape, I'm not sure what, K0, so that the polygon will be almost guaranteed to be very close to that shape? And the answer is yes, and this was really what motivated this question is what motivated the more refined bounds on the number of lattice polygons that I mentioned earlier. And the theorem is that there is a convex body for any body k. Well, I guess in this case, this is for the unit square. So for the unit square, there exists a limit shape. In the sense that the probability that the Hausdorff distance between a uniformly random convex polygon and the limit shape is greater than epsilon will tend to 0 for any epsilon greater than 0. So what is Hausdorff distance? Just is you take your two curves, and for one of the curves, you go along each point and say, what's the furthest distance to the other curve? And that gives you some number by taking the supremum over those. And you do the same thing for the other curve. Now you have two numbers, and you take their maximum. So it's, in some sense, the furthest distance between any 2 points in the curve. Or to put it another way, we can put a little narrow band around this limit shape, and we can be fairly confident that as long as n is large enough, our uniformly random polygon is going to lie inside of that band. Bárány's proof actually applied for any convex body, so it's not restricted to the unit square. So a kind of obvious question, I think, is the three-dimensional theorem of this, or three-dimensional generalization of this, or three-dimensional analog, I guess, of this question true, or the d-dimensional generalization? But we don't know, so, and not for lack of trying. To put it another way, if you take, say, a uniformly random polyhedron in the square n by n by n, and then scale it down to the unit cube, does the analogous property hold? Is there a limit shape there? And this is an open question. So that's kind of the starting point for my the work that I did with Bárány and Julian Barreau. But we weren't able to solve the full question about polytopes in d dimensions. So what we do instead is consider a restricted set of polytopes, the zonotopes. And what I'm going to talk about is zonotopes with a given endpoint that are contained in a fixed cone. So a zonotope is a polytope that's generated by a set of vectors. And how you generate it is you take coefficients in the range 0 to 1 and multiply it by all the vectors. So it's some convex polyhedron with this special property that it has this set of generators. So here's an example. Here are 3 generators in the plane. And if you take the sums of each with coefficients ranging from 0 to 1, you get this convex body. And the most extreme point from 0 is just if we take all the coefficients to be 1, we get the end point of our zonotope. And you can see in the plane that lattice zonotopes are exactly corresponding to convex chains, because here we take our generators, we sort them by slope, and that gives us the lower boundary of the zonotope. And so there's exactly a one-to-one correspondence between zonotopes contained in the positive orthants and lattice convex chains with the same endpoint. And convex chains with restricted choice for slopes were considered in these earlier papers. So let's denote by T of C comma K, the set of zonotopes in a given convex pointed cone C with a given endpoint K. And P of CK is the number of such zonotopes. For example, if we take C to be the positive orthant in the plane and K to be the points NM, then the P of CK in this case is exactly the number of convex lattice chains connecting 0, 0 to N comma N. The first theorem in our paper is that for any cone and endpoint, there's this quantity that depends only on that Q and endpoint K. And I'll discuss, this has some geometric meaning that I'll discuss a bit later, such that as n tends to infinity, the log of the number of zonotopes in C with endpoint N times K tends to some constant that depends on the dimension, which is here, times a constant that depends on the cone and the endpoint, which I'll discuss a bit later, times n to the d over d plus 1. And so this is a generalization of the earlier results by Bárány, Vershik, and Sinai. The second result is that we can characterize or bound the number of faces of a random zonotope. So this is the first part of saying what does a random lattice zonotope look like? The answer is that for any I, so if f sub I is the number of I-dimensional faces of a zonotope, so vertices, edges, all the way up to facets, the ratio of this to n to the d times d minus 1 over d plus 1 is bounded between two constants. And clearly, if you wanted a more refined result, you would have to have different, the constants might have to depend on the parameter I. But since we're unable to unable to really determine the asymptotics of the log for any I, we just give two different constants that will cover all of the, that will cover it for all dimensions. And similarly, the same bound applies for chains, or flags, I'm sorry, where you take a vertex inside an edge, inside a two-dimensional face, inside a three-dimensional face, etc.
So presumably C1 and C2 are more or less the same.
I think that there should be, for any fixed I or for the number of flags, there should be a constant. Yes, I think so. Yeah, it seems so. Yeah, I think it should be. And so I say close the gap between C1 and C2, but obviously if you were to do that, you would have C1 and C2 would then have to depend on exactly which problem you're dealing with. The only reason we get away with only using two constants here is because our bounds are quite crude.
Can I? So in the first equation, you have Fi, but no other places that mention I.
Yeah. So I is just any integer that you could put in for the I. So it has to be bounded between 0 and d minus 1.
Right. So this number of I-dimensional faces independent of I.
It's not independent of I, but it is independent of I at the level that if we choose C1 small enough and C2 small enough, and we're looking at the exponent, because, well, I guess no, wait.
I expected you might have n to the I something.
No, there's not. There's not. And it's kind of, right, if you think about kind of a generic polytope, then this is saying that the faces aren't too complicated. This is what you would expect if the complexity of the face depends only on the dimension and not on n, right? Because you look at some, say the faces are all hypercubes, then the number of vertices on a facet is 2 to the d minus 1. But d minus 1 doesn't, 2 to the d minus 1 is just a constant. Yeah.
Does this CI depend on D or, I'm sorry?
The C's depend on the dimension, yes.
Yes, the D.
Yeah, absolutely.
So it says,
so somehow the dimension is hidden inside choosing the cone here and the endpoint in the statement of this.
it says mostly the number of.
Actually, CI and CJ really depend on the cone and the endpoint and the dimension. It depends on everything except for n. So here's the kind of coolest result, I guess, is the existence of a limit shape. So for any cone and endpoint, there's a convex body T0 such that the uniformly random zonotope with that endpoint inside that cone is close to the fixed limit shape. And so this is really the generalization of the theorem that I mentioned earlier in the point. Well, it's not quite, because we're talking about the end point in a cone, whereas the previous one said, what does a polygon inside a square look like? And there wasn't any mention of a endpoint or slopes. And so we do get, for the special case of the hypercube, we do get kind of the proper generalization of the theorem that I mentioned. So it's still open to show that there's a limit shape for zonotopes contained in an arbitrary convex body. But we did manage to do it for the hypercube.
Is it look similar to the general case when
Yes, yeah, it looks the same. At least for the square, right? We don't have for an arbitrary body. Right. So let me discuss in particular, for the square, the limit shape is you basically take a parabolic arc and connect each of the midpoints of the square like this. And this is corresponding to finding those arcs that have the largest number. Yeah, this is the limit shape there, and it's the same. It's the same whether you have a zonotope or but I'll discuss a little bit more of the geometric meaning for the quantity Q, and also what is the limiting zonoid actually. So here's a cone. The dual cone is given a convex pointed cone C. The dual cone C the dual cone is the set of all vectors that have positive inner product with any, or positive dot product with any vector inside of our cone C. I don't know if we actually need the dual cone here, but we do need section. So given a cone C and a vector U, a section of the cone, or those points in the cone that have a fixed, the section of the cone C of U is equal to T is this subset of the points of C that have a fixed dot product T with U. So in general, it is going to be some perpendicular to U. It's not necessarily going to be lined up with U in this sense. This is just drawn a certain size for visibility. And a cap is the area underneath a section, in the sense that the cone has a point. The section is the intersection of the cone with a hyperplane. And there will generally be one side of the, I mean, except there could be degenerate cases, but typically there'll be some area that's underneath the section. So we're going to rely on old results. So given a point in the interior of a cone C, there's a vector in the dual cone such that our point K is the center of gravity of the section U of C of U is equal to 1. So we need, if you think about the K being a vector here, the inner product of K with U has got to be equal to 1, which is why in this case, if you imagine that K is quite far from the origin, U had better be pretty small, because K is contained in this section. And furthermore, K is the center of gravity of the section. This is not using lattice here. This is just a purely geometric result. And furthermore, the cap defined by this section is the unique cap of minimal volume that contains K. So now we define lambda. So now we have a K, U, the choice of U depends on K. We define lambda so that when we integrate x dx over the cap, we reach K. And we'll define, my cap seems to have disappeared, but oh. I think other people have had this problem before as well, because there should be a shaded cap there.
It's not the problem of the projector.
It's not the problem of it. Oh, I see it here.
I can see over the monitor.
Yeah, you can see it there.
Interesting.
So we have some cap Q. And this is just, if we integrate x dx over this cap Q, we're going to reach K. And Q is defined in this way using our vector U that we got from Gauguin's theorem. And so this number that I said earlier depends on, had some geometric meaning, is the volume of this cap Q, which we can compute from a given cone and end point. So the claim, an interesting geometric claim is that for any subset of our convex cone C that's not equal to, I guess Q is the unique cone of maximal volume, or the unique subset of C with maximal volume such that when we integrate over that subset, we reach K. And the idea here is pretty simple. Let's suppose that we have some set S that we want to compare, and suppose that integrating over S also, suppose that we also have its integration over S. is equal to K. Well, we know from the assumption, from kind of the definition of Q, we know that if we look at any point here in Q minus S and any point in S minus Q, that, well, this point Y, the inner product of Y with U is less than lambda, or at most lambda. An interproduct of, let's call it Z, or the dot product of Z with U is greater than lambda. So what we do is, well, we know that when we integrate over the Q minus S, it has to be equal to the integration over S minus Q, because the integration over S is equal to the integration over Q. But on the other hand, for every point on the left, the integrand is larger than it is for any point on the right. I'm sorry, smaller than it is for any point on the right. Each of these points is upper bounded by lambda, and each of these points is lower bounded by lambda. So if we take n to be very large and look at then we can approximate this integral by summing over the lattice points. And it's pretty easy to see, I think, that the error in this approximation depends on the boundary of our set Q, and it depends on n. And as we take n larger, this error will get smaller. And so this is kind of, in some sense, the largest set of vectors that's going to give us the point K as the largest set of vectors inside this cone C that gives the correct endpoint are exactly those vectors that are contained in this cap U. And it turns out that the limiting zonoid is just the limit as n goes to infinity of the convex chains that you'll get from, or the zonotopes that you'll get by taking exactly this set of generators, which are the generators contained in that cap. But that's not a proof. That's not a proof, but it does give you a geometric characterization. It's not a proof that this is the limiting zonoid, but it is a characterization of the limiting zonoids that you can use to calculate what they look like. So in the plane, this is what they look like. You have two parabolic arcs from 0 to 1, 1. Here, I'm just taking the cone to be the positive quadrant and the endpoint to be 1, 1. And you can do the same thing in R3. Take the cone to be the positive orthant, take the endpoint to be 1, 1, 1. And the zonoid, it turns out, has 6 pieces that are, 3 of them have equations. X plus y plus z is equal to 3 times the cube root of x times y, 3 times the cube root of y times z, 3 times the cube root of x times z. So those are 3 of the surfaces. And the other 3 surfaces you get by reflecting over the center of the zone. And in theory, you can kind of use the proof that I just described to calculate what the limiting zonotope is, or limiting zonoid is for any given cone and endpoint, in principle. So the proof of that there exists a limiting zonotope we get from a probabilistic model. It's a generalization. I mentioned that there were 3 different proofs given in the 1990s of the existence of a limiting zonotope for the plane by Bárány, Vershik, and by Sinai. And this is a generalization of Sinai's proof, which uses a kind of probabilistic model that I'll describe now. So it's a nice probabilistic method proof. So the first thing that we're going to do is we're going to use the correspondence between zonotopes and functions from primitive vectors. So a vector we're going to say is primitive if the GCD of its coordinates is 1. And here we're only taking the GCD of non-zero coordinates. So in particular, the GCD of the origin 0, 0, 0, 0 is not primitive, but 0, 0, 0, 1 is primitive. Is that okay? So what we're going to use is a correspondence between the space of zonotopes and the space of positive integer valued or non-zero integer, non-negative integer valued functions on the primitive vectors that are contained in our cone C. So the function associated, if we're given a zonotope and we have this set of generators, what we do is take each generator and look at the smallest primitive vector that's contained in it, and it will be some multiple of that primitive vector, and we simply add that number to the value of the function at that point. So here's an example. Here we have a zonotope with the generators 1, 3, 2, 2, and 4, 2. 1, 3 is primitive, so we don't need to do anything at all. 2, 2 is not primitive. The primitive vector that's contained in it is 1, 1. It's 2 times 1, 1. And 4, 2 is 2 times 2, 1. And if we had, say, 2 vectors in the same direction, which is perfectly acceptable, we simply do the same thing for each one. We just take the smallest vector that works. And there will be some... So this... Since, in general, this function, if we didn't use primitive vectors, the function wouldn't be invertible, but since we do, it is. So let's see, we've shown how to take generators of a zonotope to a function, so now we're just given a function and we need the zonotope, and this is very simple. We just take those generators with a given multiplicity. You have a function on the primitive vectors, and if the value of a vector is k, you simply take that as a generator with multiplicity k, and that gives a zonotope, or the correct zonotope. So picking a zonotope with the correct endpoint is equivalent to picking a function such that the sum of when we sum over the domain, we get this point n times k. And we can define a probability distribution on the space of functions, the space omega of non-negative integer value functions on the primitive vectors contained in the cone. And it's exactly this, where recall that, oops, I'm hitting the wrong button here. Recall that P of C comma n times k is the number of zonotopes with this endpoint contained in the cone C. And, well, if you look at a function and the endpoint is wrong, then the probability is 0. And if you look at a function and the endpoint is right, then the probability is 1 over the number of candidates. So this is just by definition the uniform distribution on zonotopes. We have a problem, which is that this distribution is not easy to handle because it's not a product distribution. If you know that there's some collection of vectors that doesn't end up to k is, if you know the support of some of the points, I'm sorry, if you know the value of at some points of a function, then this tells you a lot of information about what the value of the function ought to be at the remaining points. There's no independence between the value of the function at the different points. So what we need, or the technique is to introduce a new probability distribution P of n that's easier to analyze, and I'll point out exactly what the good properties are. So this is a generalization of the probability distribution that Sinai introduced to solve the two-dimensional case. So here's the distribution. I'm not going to try to explain where it comes from. For me, this is somewhat magic, but I think that some people do understand how to come up with the right distribution. But there are some good properties. First of all, the probability that a given function is, the probability of a given function under this distribution on functions depends only on the endpoint of the function. The endpoint, so recall that x of omega is the sum over all primitive vectors of the omega of x times x. So I can write it down. X of omega is sum over x of omega of x times x. And one good feature of this is that the probability of choosing a given function, it depends only on the endpoint. Because z of n, this kind of normalizing constant out front, is always the same. So the only place that omega shows up in this equation is as the argument of x of w. So in particular, if we say choose the right endpoint, n times k, then the probability of, then P of n conditioned on having the correct endpoint is the uniform distribution on the zonotopes that have the correct endpoint. And this is, so if we can show that this probability distribution has very good properties that we want, and that the probability of getting the right endpoint isn't too small, then hopefully those good properties will be inherited by the uniform distribution on the zonotopes that we're interested in. The second good property is that this is actually a product distribution, in the sense that here we can think of omega of x as being a random variable. You fix a point, choose a function from the distribution P of n, evaluate that function on the point. This gives you some distribution this gives you a random variable omega of x, and these are independent. For the distribution Q of n that we're actually interested in, really the big problem is that these are not independent random variables. If you know what the evaluation of a function is at a given point x, this tells you a lot of information about what its evaluation is at different points. Under this distribution P of n, that's no longer true. You can tell me what the value, you choose a function from P of n, tell me what the value of omega is at half the points. I still can't tell you anything at all more than I originally knew about the value of the function at the remaining points in the code. Of course, there's an infinite number of points, but just by the way that this is chosen, almost surely any function that you choose is going to have finite support. So the kind of key lemma that allows us to connect our distribution P of n with the distribution that we're interested in Q of n is this local limit result. And I'll just show how it applies for one of the, I'm not going to give any proof of a result here, but I'll show kind of how this local limit result plays into determining the number of zonotopes. So if you recall, here is the first theorem that I showed in our paper. So for any cone C and endpoint K, there are constants Q and C sub D, where Q depends on the cone and the endpoint, and C depends on the dimension only, such that the log of the number of zonotopes in that cone with that given endpoint is these constants times n to the d over d plus 1. And this is the limit as n goes to infinity. I don't know what happened to that notation, but it should be say limit as n goes to infinity. So I'm not going to really show the proof of this, but I'll show how the local limit result plays into it. So we know I think I put this up on the screen earlier, but the probability that given endpoints occurs under the probability distribution P of n is just the number of zonotopes with that endpoint divided by this partition function z of n, which is the normalizing constant, times e to the minus beta u times n. So if we take logs here, we get that the log of the quantity that we're interested in, which is the same thing that we're trying to bound here, is equal to 3 terms. First, the log of the partition function plus n times beta n times u dot k plus log of the probability of getting that end point. Well, for what we showed is that for this, so this is true. Okay, so I switched from m to n times k, but this would be true if every place it says n times k, you write m. That's still true. This formula is true for an arbitrary point m. But at the special point n times k, we have this weak local limit result, which is that this term here is bounded above by little o of n to the d over d plus 1. Now these two terms, it turns out, this one exactly from the definition of beta. If you just plug the definition of beta in here, you can see that this is a term is of order n to the d over d plus 1. And this one is quite a lot of work to bound. And I'm not going to show how to do that. It's quite a lot of work to bound, but it is also order n to the d over d plus 1. And so in particular, I think one thing that we're thinking about is maybe if you can get, instead of a weak local limit result, something better, then you can get a better, maybe we can generalize Barreau and Enrique's bound, two-dimensional stronger bound on the number of zonotopes to arbitrary dimension. Because what we have now is the weaker 1 plus the lower 1 bound.
Is there any randomized algorithm for some integer programming
solution inside the limit shape of the Zonotopes?
Oh, I don't know about that. Is there a problem, a natural problem? Yeah, I don't know if there's like algorithmic applications of determining this zonoid. I gave the history that I know, which is that it's a kind of natural geometric question that arose studying this question of Arnold back in the 80s. So I don't know of any algorithmic applications. Yeah.
For the general case, you said in the beginning, like when you are between 0 to n in 2 dimension, so the limit shape exists. So do we know the equation of the limit shape?
Yeah. So it's in the two-dimensional case, the limit shape is characterized in the general polygons. In the two-dimensional case, the limit shape is characterized for any shape. If you fix.
So for any shape, we like it's not existence proof. It's like we know the.
It's actually we know exactly what the limit shape is. For the square, I had it drawn here before. It's like this. I mean, this is the limit shape for the square, and in general, there's something called the affine perimeter. Definition is escaping me at the moment, but you take the body with the largest affine perimeter. The limit shape is the shape that has the largest affine perimeter that's contained in your given shape, and it's known to be unique. It's known to exist. I think in higher dimensions, it's known that there is a body with the largest affine surface area, but it's not known to be unique. And this is.
So in higher dimension, is there any like conjecture? What should be the limit shape exist, or like is there?
I mean, I would say, Mike, and I don't see any. In 2 dimensions, the zonotopes and the zonotopes and polygons have the same limit shape, and as far as I know, it should be the same in higher dimension. I mean, yeah, that would be my guess. Yes.
So for the convex shapes which approximate that shape, do they maximize the number of integer points on the boundary? Is that
do they maximize the number of integer points on the boundary? That's an interesting question. I mean, they, right.
Or does,
Yeah.
does a sequence of shapes
Which satisfy this, have the largest number of integer shapes. I think, yes, this is similar to, yes, I think so. This seems similar to what I was talking about, that for zonotopes, you take this cap, and so you have the largest number of generators. And it should be, you have it's kind of approximating what you're doing for the zonotopes is you're approximating the zonotope that you would get by choosing the largest number of generators that you could possibly choose and hit the right thing. So that, I think that's related, and it should be true, but
I'm wondering if there's a difference between taking sort of maximal collections of points in convex position as opposed to a random set of points in convex position. Because like the one with the largest perimeter will have the most subsets as well.
right.
And these will sort of have the same shape. But I don't
You know,
think
I'm
that's
not. So I think actually maybe if you took the whole thing, like the whole
sure, that's
square,
fine.
you'd actually get more. It's
Yeah.
somehow a question of you're getting. But these are like very degenerate in the sense that they're on straight lines. So it's a little different than the largest number of points.
okay, that's good.
Yeah. So the answer is no. It doesn't have the largest number of points, but what it has is. I mean, yeah. The geometric property that it has is that
I guess
if you
maybe
take
in general position, you put that condition.
right, yeah, it is a kind of general position thing, but it's not. I mean, again, I'm not sure exactly what the condition is other than the one that I said. You are going to have like there will be points on lines inside this cone, right? You're going to have many of your vectors are going to have the same direction. It's just So they're not really like, right? So if you take some cone like this and you look at, here's your grid. In particular, there's a lot of points here, and your first vector is going to be like out like that, and then you're going to have something like this, like that, you know. But this one is like, well, you got 1, 2, 3, 4, 5, something like this. Right.
Any other questions?
So, what do we know the limit shape of limit shape of DQ? Not.
We don't. So for zonotopes, yes, we do know. That's in the paper, and I showed it for. No, I guess I showed the endpoint version, but it's somewhat similar to this. But for polyhedron, we know basically nothing in dimensions 3 and higher. Like for general polyhedron, for this question, there's nothing is really known. And I mean, it's somehow there isn't a very good. If you get a general polyhedron, there's not really a very good decomposition of the surface into chain-like things. So the techniques just don't work. And you need some new idea.
Any other questions? Let's